Hello students, good evening. Welcome to the YouTube live session from ACE Engineering Academy. I am Achyuth Bhure and today I am going to cover linear momentum equation topic. Okay? So linear momentum equation, it can be applied for small differential volume. So if you apply linear momentum equation for small differential volume, you'll get equations like Euler's equation and Navier-Stokes equation. Now today we are not going to apply this equation for small differential volume, but we are applying it for a control volume. So what is control volume? Control volume means region under observation. So this control volume may be fixed or it may be living. It is just region under observation. So fluid may enter the control volume and fluid may leave the control volume. Okay. Now we are going to apply momentum equation. Momentum equation means Newton's second law. So as per Newton's second law, summation of all forces is equal to rate of change of linear momentum. Correct? So this is Newton's second law. Now here, this left hand side indicates vector sum of all forces which is acting on the fluid which is passing through the control volume. Okay? So this is vector sum of all forces acting on the fluid. Whereas the right hand side represents momentum change, rate of change of momentum for the fluid. See, this right hand side, it is little difficult to calculate for the fluid. Why? Because fluid moves in a complex manner. For example, let us consider at time t, fluid is matching the control volume. Okay? Whereas after some time, the fluid will move in complex manner, something like this. So this is initial position of the fluid, which is matching the control volume. Whereas after some time, fluid will move away from the control volume. So some of the liquid is going out of control volume and some of the fluid is here entering inside the control volume. Now, the rate of change of linear momentum, it means momentum of the fluid for time t plus dt minus momentum of the fluid at time t divided by dt. So this limit dt, it should be very small. So dt should be 10 to 0. So final momentum minus initial momentum divided by dt, that is rate of change of linear momentum. As the shape of fluid is complex here, so this thing is little difficult to calculate. And it is calculated with the help of Reynolds transport theorem. So I'll just give the final result here. The Reynolds transport theorem says, so this quantity is equal to triple integral over control volume rho into vector v evaluated over control volume. Now don't worry too much about this mathematics. Later on I am going to give you simplified form also. So this is one term. There is another term also. So this is double integral evaluated over control surface. So control surface means surface of the control volume. So this is equal to rho into v vector v dot n cap evaluated over the surface of control volume. Now, I'll just give physical meaning of these two terms. I will not go into details of mathematics, just I'll give physical meaning. Listen here. So let us consider some small volume inside this control volume. Let us say this volume is dv cut. So notation v cut I am using for volume and notation v I am using for velocity. Okay. So this volume, it will have mass equal to density into volume. Okay. Mass contained by this volume is density into volume. Now, if flow is unsteady, listen here, if flow is unsteady, then at same point at time t and at time t plus dt, velocity can be different. In unsteady flow, at the same point, velocity changes with respect to time. Am I right? So at time t plus dt and at time t, velocities will be different. That's why you will have change in momentum. Whereas if flow is steady, then at same point, velocity will not change. Then momentum for this part, it will not change. Clear? So if I take momentum for this part at time t plus dt minus at time t, that term, that difference will be 0 if flow is steady. Okay. If it is unsteady, then definitely it will be non-zero. So this first term indicates momentum change. This indicates momentum change within control volume. Within control volume. And here we are taking derivative with respect to time, so it indicates rate of change of momentum happening inside the control volume, right? Whereas this last term is evaluated over the surface. This is a surface integral. So what is meaning of that? It means, see, in time dt, some fluid is going out of control volume and some fluid is entering inside the control volume. So this indicates how much momentum flux is crossing the control volume. Okay? This indicates momentum flux crossing the control volume. Momentum flux crossing the control surface. Control surface. This is evaluated over the control surface. Now students who are good at mathematics, they may be knowing that V dot n, this indicates normal vector. Let us consider here I have taken small area dA. So this red one is small area dA. So this is dA. So V dot n, if you do, you will get normal component of velocity. Now normal component of velocity into area will get discharge which is going out of this area. Okay. So discharge into rho into V. So this will get momentum flux going out of that area, and this thing is calculated over this entire surface. So this second term indicates momentum flux crossing the control surface. Now some of students may not be understanding this because this is little mathematical, and that's why I'll give one simplified version. While solving problems, we are not going to use this mathematical form. I'm just telling the basis from where you'll get the equation. Because later on, students keep me asking means how the equation is coming. The equation is coming from this Reynolds transport theorem. So this comes from Reynolds transport theorem. So details of Reynolds transport theorem you can read in books like F.M. White. So Reynolds transport theorem. Now let us consider simplified version of this. Now let us imagine this is a nozzle, and through nozzle water is going out. Okay. So let us say velocity at inlet is V1, velocity at exit is V2. Now here I want to find rate of change of momentum for the fluid which is passing through this control volume. So I have considered a control volume. So this control volume, it is containing nozzle, and inside that nozzle there is liquid also, right? So it is not necessary that control volume can have only liquid. It is not necessary. Control volume may have only liquid, or it may have liquid plus solid. Both things are possible. So here this is the fluid inside control volume. So in time dt, what happens is some amount of fluid will go out. So whatever mass of fluid we are considering at time t, so this will deform. So some mass will go out, and here this portion will be occupied by some other mass, right? So same things I am showing here. This is fluid volume at time t, and this is fluid volume at time t plus dt, correct? Now we want to find out rate of change of momentum for this fluid. So rate of change of momentum d by dt of mv bar, so this will be equal to momentum at time t plus dt minus momentum at time t whole thing divided by dt. This is how we calculate derivative, correct? Right. Now let us imagine flow is steady for the time being. Let us imagine flow is steady. If flow is steady, then at any particular point velocity will not change, right? So at time t and at time t plus dt, at these 2 points velocity will be exactly same. So it means what? It means if flow is steady, then momentum corresponding to this common portion, it will get cancelled. So momentum corresponding to the common portion will get cancelled. This happens in steady flow. So what remains? So we'll get momentum corresponding to this white region and this blue region. What we are doing is, we are doing final momentum minus initial momentum. So for common portion, momentum is cancelled. But momentum corresponding to this white portion and momentum corresponding to this blue portion, it will not get cancelled. Okay. Now let us imagine mass flow rate which is going out is m dot. Okay. This is the mass flow rate. So in time dt, the mass which is going out will be m dot into dt. Agreed? If m dot is mass flow rate, in time dt, m dot into dt mass will come out. And this mass will carry some momentum. Momentum will be mass into velocity. So momentum corresponding to this mass will be m dot into dt into velocity at exit. So exit velocity is v2. Now this term is positive because final momentum minus initial momentum we are doing. That's why this term is positive. From this momentum we are subtracting momentum at time t. So momentum corresponding to this blue portion, this will be negative because we are subtracting initial momentum here, right? So this momentum will be negative. Now mass which is going out will be same as, mass which is coming in, it will be same as mass which is going out. So that's why mass corresponding to this blue portion, it will be again m dot into dt. So momentum corresponding to this mass will be mass into velocity. Velocity here is v1. Right? So here velocity was v2. So if flow is steady, momentum corresponding to this common portion is cancelled, and what remains is momentum corresponding to this white portion and blue portion. So this negative momentum I am writing here, m dot into dt into v1. Whole thing divided by dt. Now this dt, it will get cancelled. So what we get is m dot into v2 minus m dot into v1. So this m dot into v2, this represents momentum flux going out of control volume, and m dot into v1, this represents momentum flux going into the control volume, right? So same thing I can write as m dot into v out minus m dot into v in. Correct? v2 means outlet velocity and v1 is inlet velocity. Now this is story in steady flow. If flow is unsteady, then momentum corresponding to this common portion, it will not get cancelled out. So because of that, you will get one extra term. So that extra term is dou by dou t of mv bar inside control volume. So this term represents rate of change of momentum within control volume. And please remember, if time dt is very small, then this common volume will be nearly equal to the control volume. So the last term represents momentum change happening inside control volume. And point to note here is, on top of this m there is no dot because derivative with respect to time is outside. So there is no dot here. If flow is steady, then definitely the last term will be 0 and you will get rate of change of momentum equal to m dot v out minus m dot v in. So your linear momentum equation becomes vector sum of all forces is equal to m dot v out minus m dot v in plus dou by dou t of mv bar inside control volume. So here this first term represents momentum flux crossing the control surface. This represents momentum flux crossing control surface, whereas this represents momentum change within control volume. So of course it is derivative with respect to time, so it is rate of change of momentum within control volume, right? Now if you compare this equation with our previous equation, now here this first term, that is triple integral, it represents momentum change within control volume, whereas this surface integral, this represents momentum flux. So if I compare this term with our equation, then m dot v out minus m dot v in, it is like a double integral, whereas this last term is like triple integral. Okay? Right. So if flow is steady, then definitely last term will be 0. If flow is unsteady, then it will be non-zero. For example, if discharge through this nozzle is constant, then in that case flow is steady. So last term will be 0. But if discharge is variable here, then this term will be non-zero. So what I have seen is, students usually don't write this unsteady term. So they will calculate only m dot v out minus m dot v in. In that case, you will get correct answer only if flow is steady. But if it is unsteady, like if discharge is variable here, you will not get correct answer. So what I recommend is, every time you have to write all three terms, then just check whether flow is steady or unsteady. If it is steady, which will be the most common case, then the last term will be 0. If you don't write this term every time, then over a period, you may forget it, there is unsteady term also. So better to write this term every time, then just check for whether flow is steady or unsteady. Another example where this last term can be unsteady is propulsion of rocket. So when rocket propels, it will throw out some exhaust gases. So mass inside rocket is changing, so m is variable there. So that flow is also unsteady flow, right? So there again, this last term will be non-zero. Now this is a vector equation, you have to take care of directions also. I have seen many students apply this equation intuitively without proper procedure or notations, then they will make mistake. So that's why I have given here systematic steps which you have to follow. So you can go through the steps, you can pause the video later on and you can note down the steps. Now I will explain the steps with the help of example. Now consider similar example. A nozzle of exit area 20 centimeter square is attached to pipe of area 100 centimeter square as shown in figure. So there is a nozzle, so exit area is 20 centimeter square, inlet area is 100 centimeter square. The nozzle discharges water into atmosphere at a speed of 25 meter per second. So exit velocity is given 25 meter per second. What is the tensile force generated in the pipe? So here we have to find tensile force generated in the pipe. Now some of students may be thinking that there can't be tensile force here, there should be compressive force, because this nozzle will act like a rocket. So when jet comes out, it will get some reactive thrust. Because of that, you will get some here compressive force. Now that thinking is not completely correct. It's true that you will get some reactive thrust, but there is another force also. The liquid inside pipe, it is pushing the liquid inside nozzle also. So because of that, you will get some forward force. Now just imagine that this nozzle is not rigidly fixed to the pipe. Okay? It is just simply kept in front of pipe. When fluid starts flowing, because of force exerted by water, nozzle will fall down now. Yes, nozzle will fall down. It means nozzle is trying to go away from this pipe. That means there must be tensile force. Okay? So that's why here tensile force is mentioned. Now sometimes they may not mention whether force is tensile or compressive. In that case, you have to decide the direction. If you are able to judge the correct direction of force, well and good. If you are not able to judge correct direction of force, then in that case, you can assume any direction, either tensile or compressive, and then follow the exact procedure which I am going to explain. At the end, if you are getting positive answer, it means your assumed direction of force is correct. If you are getting negative answer, means you have to reverse the direction. So I will demonstrate with the example. So first step here is select the control volume. Now, many students will have difficulty in selecting control volume itself. So for that, I have given here clear-cut guidelines. So you have to look for two things. Select the control volume in such a way that it intersects the unknown force to be determined. It means here we need to find out force in pipe. So control volume should intersect the pipe. Now what is logic behind that? Later on we are going to draw free body diagram of this control volume. So whatever force we want to determine, that should be present in the free body diagram. So if you are not intersecting control surface with this pipe, then that force will not come into picture. So that's why control surface should intersect unknown force to be determined. In other words, you should select the control volume in such a way that the unknown force must be present in the free body diagram, right? Second point is pressure everywhere on the control surface is known. See, when we draw the control volume and when we draw the free body diagram of control volume, there we have to show pressure forces also. So you should draw the control volume in such a way that on the control surface everywhere pressure should be known. If pressure is unknown, then you will not be able to find the required force, right? So everywhere pressure should be known. That care you should take. Now here I am selecting control volume such that it is intersecting the pipe and it is from outer side of the nozzle. Why from outer side? Because on outside everywhere I'll know what is the value of pressure. Everywhere here will have atmospheric pressure. Right. Now second step, draw the free body diagram of control volume showing all external forces. Now free body diagram means you have to detach this control volume from all adjacent connection and then you have to show all external forces. That is FBD. So I have detached it. Now let us visualize the various forces acting on the system. First is self-weight. Now this self-weight includes weight of water as well as weight of nozzle. Because inside control volume we have nozzle and inside nozzle we have water also, right? So it is combined weight. So next force is this pressure force. Now who is exerting this pressure force? Liquid inside pipe is exerting pressure on liquid inside nozzle. Correct. Then from outer side we'll have atmospheric pressure everywhere. At the exit we'll have jet and this jet is also exposed to atmospheric pressure, right? So from jet also you'll get some pressure on the front part of nozzle. And how to show the pressure? Please remember, pressure is always compressive, it is never tensile. So always show pressure arrows towards the control volume. Now some students think that here fluid is going out, so pressure should be towards right. That is not correct. Pressure is always compressive and here we are drawing free body diagram of liquid inside control volume, right? So this is pressure acting on the liquid inside control volume. And who is exerting that pressure? The jet is exerting pressure. Okay. Now still some students may find difficulty. You can think in this way. So here we have nozzle. If I want to draw free body diagram of jet part, so here on the jet you will get pressure in this direction. So liquid inside nozzle is pushing the jet in outward direction. So jet will exert equal and opposite pressure on nozzle, right? So this is, you can say, reactive pressure. I hope it is clear now. Right. Apart from this, we'll have tensile force. So this is tensile force. And please remember, this tensile force, it is not only present at 2 points, but it is present all around the circumference. So nozzle is something like this. So everywhere on the circumference you'll get tensile force. So it is not only present at 2 points, it is present at all points. So vector sum of all those tensile forces, let us say it is T. So this we are considering as T. So this force together we are considering as T. So this is the free body diagram. That's it. Next step, subtract atmospheric pressure from all sides or show gauge pressure everywhere. So next step is just a simplification. So what we are doing is we are subtracting atmospheric pressure from all sides. So why we are doing this? Because when we subtract atmospheric pressure, everywhere on outer side will get zero pressure. So in that case, we need not to bother about this outside pressure. And inside will get gauge pressure. But can we do that? Yes, definitely we can do that. We can add constant pressure on all sides, or we can subtract constant pressure from all sides. Adding constant pressure or subtracting constant pressure will not change any net force. I'll give one simple example. Just imagine that some stone is suspended in air. Okay? So air will be exerting atmospheric pressure from all sides. So everywhere pressure is constant. So due to this atmospheric pressure, this stone will not move, right? It will not move, it will stay as it is. Because these atmospheric pressure forces are cancelled out. At some places, pressure is towards right, and at some places it is towards left. If you take vector sum of all those things, you will get zero force. On our body also, everywhere atmospheric pressure is acting. But still, we don't feel that force, correct? Some of you may be thinking atmospheric pressure is small. Please remember, it is not small. Atmospheric pressure, roughly, it is 1 kg per centimeter square. It means if you take 1 centimeter square area of our skin, so it is holding around 1 kilogram mass. So that much amount of huge pressure is caused by atmospheric pressure. Still, we don't feel any force, right? We will not feel any force because vector sum of all forces is getting cancelled out. So in such case, net force is 0. So conclusion is, constant pressure will not cause any net force. So here, if I add constant pressure or if I subtract constant pressure, it means I am adding 0 force or I am subtracting 0 force, right? So let us go to next step. So we subtracted atmospheric pressure. So everywhere on outer side pressure is becoming 0, and here the pressure is becoming now here we'll get pressure as P1 minus PATM. So which is equal to P1 in terms of gauge. So that's why in momentum equation always we'll consider gauge pressures, not absolute pressure. Now some students may think that either we can use absolute pressure or gauge pressure. Answer should be same. That is true, but one common mistake students do is, so while using this momentum equation, they will consider absolute pressure at inlet and exit, but they will forget to consider absolute pressure on this side surface. That will be incorrect. If you want to consider absolute pressure, it should be considered everywhere on the control surface, not only at inlet and exit. And if you don't consider absolute pressure on the side surface, because of that there can be huge error, because atmospheric pressure is not small, it is 1 kg per centimeter square. So you'll get huge error. You can try it. So in one case, you take this control volume, you ignore atmospheric pressure, take gauge pressures, and in another case, you consider atmospheric pressure but only at inlet and exit. And if you solve for T, you will get very different value of T. So better way is always consider gauge pressure. The next step, apply momentum equation along unknown force to be determined. Only consider components of all vectors in the selected direction. Now last step is we have to use momentum equation. So I'll write here momentum equation. So our momentum equation is vector sum of all forces is equal to m dot v out minus m dot v in plus dou by dou t of mv bar inside CV. Okay. Now this equation we have to apply along the unknown force. So idea is we need to find out this unknown force T. So I should apply momentum equation in x direction, not in y direction. Because if I apply this equation in y direction, T will not come in that equation. So let us apply this equation in x direction. Okay. So before proceeding further, let us first check whether this last term is 0 or non-zero. As water is going with constant velocity at exit, discharge we can say it is constant, so flow will be steady. So velocity will not change. Now don't think that here velocity is changing inside nozzle. Of course, inside nozzle velocity will change even when flow is steady. To check whether flow is steady or unsteady, what you have to do is, you have to observe a particular point and see whether velocity is changing at a given point. Now here if you fix any point, let us say exit, velocity at exit is always 25, it is not changing. It means flow is steady. Okay. So steady flow, so last term will be 0. Now we'll consider this left hand side. So in the control volume we have 3 forces: weight, pressure force and tensile force. So out of which this weight will not have any component in x direction. So component of weight in x direction is 0. Component of this pressure force in x direction will be pressure into area. So it is acting in positive x direction. So here I am selecting x direction. So this is positive x direction. Pressure is acting in positive x direction, so plus. So plus P1 into A1. Where this P1 is now gauge pressure, okay? This is gauge pressure. Then next force is T. T is acting in negative x direction. That's why I'll write it as minus T. Equal to. Then first term is m dot into V out. M dot is scalar quantity, so no need to worry about direction. I'm writing it as it is. Velocity at outlet. So at exit we have velocity V2, and this V2 it is in positive x direction, so I'll write plus V2. Minus sign is inherent to the equation, so as it is I'm writing m dot is scalar, no need to worry about direction. Velocity at inlet, so this velocity it is also in positive x direction, so I'm writing this as plus V1. That's it. Your momentum equation part is finished. So we converted this vector equation into scalar form. Now rest of the part is just simplification. So this T we will write as P1 into A1 minus m dot into V2 minus V1. So this is expression for thrust force. Now I was talking about reactive force, right? So because of rocket-like action we'll get some reactive force. So this m dot into V2 minus V1, this represents reactive force, so which will be acting in backward direction. Whereas P1 into A1, this represents pressure force exerted by water. So usually students, they apply momentum equation without drawing proper control volume. In that case, there is good chance that they will miss this pressure force term. They will consider only this change in momentum part, right? But if you draw proper control volume and if you draw proper free body diagram, you will never make mistake. So it can be shown that this pressure force in case of nozzle, it will be always higher than this reactive force. So this T value will get always positive, right? Let us find now m dot V2 is given, m dot V1 and P1 we have to find. So m dot is equal to rho A2 into V2. So rho is 1000. A2 is given 20 centimeter square, so 20 into 10 to the power minus 4 into V2 is given 25. So if you perform this calculation, you will get mass flow rate as 50 kg per second. Then we'll find out this V1 by using continuity equation. So by continuity equation, A1 V1 is equal to A2 V2. So V1 will get A2 divided by A1 into V2. So A2 is 20, A1 is 100 centimeter square. So both I am writing in centimeter square. So into 25. So this you will get 5 meter per second. So we found V1 and m dot. Now pressure needs to be found. So pressure we can find by using Bernoulli's equation. So by Bernoulli's equation, so we'll get P1 by rho g plus V1 square divided by 2G plus Z1 is equal to P2 by rho G plus V2 square divided by 2G plus Z2 plus losses. But in the question, it is mentioned that neglect the losses. So HF we can take 0. So as nozzle is horizontal, Z1, Z2 same. Pressure at exit, it is equal to atmospheric pressure. But we are considering gauge pressure, so atmospheric pressure becomes 0 in terms of gauge. Right? So we are left with only 3 terms. Pressure term, velocity term, and velocity term on right hand side. So if you simplify this, you'll get P1 equal to rho by 2 into V2 square minus V1 square. So this pressure you'll get simply change in dynamic pressure. 1000 divided by 2 into 25 square minus 5 square. So if you perform this calculation, you'll get 300 kilopascal. So this is gauge pressure. Because atmospheric pressure we have taken 0. Now substitute these values in this momentum equation. Let us say this is equation number 1. So T is equal to 300 into 10 to the power 3. A1 value is 100 centimeter square. So 100 into 10 to the power minus 4 minus m dot is 50. V2 is 25 and V1 is 5. So if you do this calculation, you'll get T exactly 2000 Newton. Okay. Now point to note is T we got positive. It means assumed direction of T is correct. So by chance, if you are not able to judge this direction of force, if you apply compressive force, but if you follow correct procedure, then compressive force here, it will be in this equation, it will be plus T. So here sign will change, here it comes minus T. So you'll get negative answer. Understand? So if you are getting positive answer means your assumed direction is correct. If you are getting negative answer means you have to reverse the direction. Now let us consider one more question. Now this is previous GATE question. It was asked in GATE chemical engineering. The figure shows idealized view of a return elbow or U-bed, which is connected to 2 pipes by flexible hoses that transmit no force. So this bend is connected to the pipe by these flexible hoses. So they are not transmitting any force. It means if I cut those hoses here, I will not get any tensile force there. That is the meaning. So water with density 1000 kg per meter cube flows at velocity 10 meter per second through the pipe which has uniform ID of 0.5 meter. The gauge pressure at the points 1 and 2 are 304 kilopascal and 253 kilopascals. Now point to note is gauge pressures they have given and we need gauge pressures only. Okay. The horizontal force F required to keep the elbow in the position is, so this F force we have to find. Right. So first step is select control volume. So how do I select control volume? So first of all, this force should come into picture. So control volume should be passing through this point. And I should select control volume from outer side because on outer side everywhere atmospheric pressure is present, which we know. And atmospheric pressure we can take 0. So I'll select control volume from outer side. Then the left hand side of control volume, I will pass through this flexible hose so that the tensile force is 0. Please remember, so wherever we intersect control volume to pipe here, we are intersecting control volume to the pipe. So here the tension force will come into picture, right, in FVD. But in case of these flexible hoses, so if I pass control surface through this flexible hose, I will not get tensile force. Something like this. So in the free body diagram, now I will directly show gauge pressures only. So in the free body diagram, we will have this external force F, weight of the entire system which will be passing through CG, and we will have pressure forces. P1 into area at inlet and P1 into area at exit. Sorry, P2 into area at exit. Now please remember, don't think here this pressure should be towards outside because fluid is going out here. This is the direction of flow, right? This pressure is always compressive, as we discussed earlier. So always show pressure forces towards control volume. So we'll apply momentum equation now. So momentum equation is vector sum of all forces is equal to m dot v out minus m dot v in plus dou by dou t of mv bar inside control volume. Now check for this last term. Check whether flow is steady or unsteady. As flow is going with constant velocity, at each point velocity will be constant. It will not change with respect to time, correct? So this flow will be steady. So last term will be 0. Reason flow is steady. Now we'll apply this equation in x direction because unknown force is acting in horizontal direction. So let us apply equation in x direction. So in horizontal direction, component of weight is 0. Then force is acting in negative x direction. So let us say this is positive x direction. So force is acting in negative x direction. So minus F I should write. P1A and P2A both are acting in positive x direction. So both should be plus. P1A plus P2A. So this is your left hand side of momentum equation, summation of all forces. So this is equal to m dot v out. So m dot is scalar. Velocity magnitude is same everywhere and that magnitude is v. Because cross-sectional area is same, so everywhere velocity will have same magnitude. Now at exit, this v is going in negative x direction. That's why I should write minus v. Then this minus sign is inherent to the equation as it is. M dot is scalar, no need to worry about direction. Velocity at inlet, it is in positive x direction, so I should write plus v. So simplify for force. So this will be equal to P1 plus P2 into A plus 2 times of m dot into v. Check it, correct? So this I am shifting on right hand side and these two terms left hand side. So they will become positive. So everything is positive, right? So P1 plus P2 into A plus 2 into this m dot, I can write rho A into V. This is m dot into V. So A I can take out. So it is P1 plus P2 plus 2 times of rho into V square. Now substitute the values, you will get answer. P1, P2 is given. So P1 is 304 and P2 is 253. Area is not given but diameter is given. Here ID means inner diameter. Inner diameter is given 0.5. So F equal to, so area will be pi by 4 into 0.5 square. P is 304 into 10 to the power 3. It is given in kilopascal. And both of them are gauge pressures, right? So we have to consider gauge pressures only. So this is 253 into 10 to the power 3 plus 2 times of rho. Rho is 10 to the power 3 for water and velocity is given 10. So 10 square. So if you perform this calculation, you will get this 5945.5 Newton, right? So this is the procedure for momentum equation. So I have explained this with 2 examples. I hope you have understood this. So this is the end of our today's session. Thank you very much. खत्म करो.
who are preparing for GATE exam will be that you should have a very clear plan and strategy, like how you have to approach the exam, and also believe in yourself and do hard work, because if you have a very good plan and clear strategy and if you will work hard, you will definitely achieve your goal. Thank you. My name is Gaurav Kumar. I have secured All India Rank 1 in GATE 22 in Electrical Engineering. I was enrolled in ACE Academy offline coaching. The ACE Academy really helped me develop a strong basic required for GATE exam. I was also enrolled in ACE Academy online test series. The questions in ACE Academy online test series were very good and helped me develop a strong temperament required for the exam. My tips for the future aspirants who are preparing for GATE exam will be that you should have a very clear plan and strategy, like how you have to approach the exam, and also believe in yourself and do hard work, because if you have a very good plan and clear strategy and if you will work hard, you will definitely achieve your goal. Thank you. My name is Gaurav Kumar. I have secured All India Rank 1 in GATE 22 in Electrical Engineering. I was enrolled in ACE Academy offline coaching. The ACE Academy really helped me develop a strong basic required for GATE exam. I was also enrolled in ACE Academy online test series. The questions in ACE Academy online test series were very good and helped me develop a strong temperament required for the exam. My tips for the future aspirants who are preparing for GATE exam will be that you should have a very clear plan and strategy, like how you have to approach the exam, and also believe in yourself and do hard work, because if you have a very good plan and clear strategy and if you will work hard, you will definitely achieve your goal. Thank you. My name is Gaurav Kumar. I have secured All India Rank 1 in GATE 22 in Electrical Engineering. I was enrolled in ACE Academy offline coaching. The ACE Academy really helped me develop a strong basic required for GATE exam. I was also enrolled in ACE Academy online test series. The questions in ACE Academy online test series were very good and helped me develop a strong temperament required for the exam. My tips for the future aspirants who are preparing for GATE exam will be that you should have a very clear plan and strategy, like how you have to approach the exam, and also believe in yourself and do hard work, because if you have a very good plan and clear strategy and if you will work hard,